Welcome back to Curious Minds. Today, we're diving into something truly amazing, something that feels like science fiction but is happening all around us.
We're going to talk about how computers see. Yes, you heard that right. How they look at a picture or a video and understand what's in it, even though they don't have eyes like we do.
That sounds impossible. I mean, I look at a picture of a dog and I instantly know it's a dog. I don't even have to think about it. How could a computer possibly do that?
That's a fantastic question, Alex, and it gets right to the heart of what we're exploring today. Because here's the big secret. When a computer sees a picture, it's not seeing it the way you or I do. It's doing something much more fundamental, much more mathematical.
Mathematical? So it's not really understanding in the way my brain understands?
Not at all in the same way. Think of it like this. When you see a delicious chocolate chip cookie, you just know it's a cookie, right? You recognize its shape, its color, the way the chocolate chips peek out. It's instant.
Oh, yeah. I definitely know a chocolate chip cookie when I see one. Sometimes I even smell it first.
Exactly. But what if you had to explain what a chocolate chip cookie was to someone who had never seen or tasted one before, and all they could do was count things and follow very precise rules? You couldn't just say it's a cookie.
That would be tricky. I'd probably say, well, it's round, usually golden brown, maybe a little bumpy, and it has these dark spots all over it.
You're getting warmer. Those dark spots and round and golden brown are exactly the kinds of clues a computer uses. For a computer, seeing isn't about intuition or recognizing a whole picture instantly. It's about counting things and finding patterns.
Counting things? Like counting how many chocolate chips there are?
You got it. And counting how many round bits, how many brown bits, how many bumpy bits. It breaks everything down into tiny, tiny details, assigns numbers to those details, and then looks for specific combinations or patterns of those numbers.
So when a computer sees a cat, it's not saying, oh, that's a cute, fluffy cat. It's more like, I'm counting 2 pointy shapes at the top, 2 round shapes for eyes, a smaller triangle for a nose, and a whole lot of fuzzy texture around it. And based on all my previous experiences, these counts and patterns strongly suggest cat.
Precisely. You've nailed the core concept. It's like a super smart detective who can only count things and compare lists. We call this whole field computer vision.
Computer vision? So how does it even start counting? A picture isn't made of numbers, is it? It's colors and shapes.
Ah, that's where the magic of turning the world into computer-understandable language begins. Let's think about a photograph. When you look at a photo on your phone or computer screen, it looks like a continuous image.
Right, like a window into another moment.
But if you zoom in really, really, really close, what do you start to see?
Little tiny squares of color, like a mosaic.
Exactly. Each of those tiny squares is called a pixel. And here's the key. A computer doesn't see red or blue the way we do. For a computer, every single one of those pixels, with its unique color, is represented by a number or a set of numbers.
Wait, so a bright red square is a number, and a dull blue square is a different number?
Absolutely. Think of it like this. When you're building with Lego bricks, each Lego brick has a specific color and shape, but for a computer, it's like each brick also has a secret serial number etched on it that tells the computer its exact shade of blue or green.
So a whole picture is just a giant grid, a massive spreadsheet of numbers?
That's spot on! Every single picture, no matter how complex or beautiful, is broken down by the computer into this grid of numbers. This is the computer's raw material, its starting point for seeing. It's like giving an architect a giant pile of individual Lego bricks, each labeled with its exact dimensions and color code. The architect doesn't instantly see a house, just a mountain of data.
Okay, so the computer has this giant list of numbers, but how does it go from a list of numbers to knowing there's a cat or a chocolate chip cookie in the picture? That still feels like a huge leap.
It is a huge leap, and that's where the clever part, the finding patterns bit, comes in. Once the image is turned into numbers, the computer starts looking for specific combinations of those numbers. We call these combinations features.
Features? Like what kind of features?
Think back to our Lego analogy. You have millions of tiny colored Lego bricks, right? What do you do with those bricks to start building something recognizable?
Well, I'd probably start putting similar colors together or connect bricks to make a flat base or maybe build a wall.
Perfect! You're starting to identify simple features. For a computer, these features are things like edges, corners, blobs of color, or areas with a specific texture. Imagine our architect from before. They don't just see a pile of bricks. They can be programmed to look for a straight line of blue bricks here, or a circular arrangement of green bricks there, or a rough patch of dark gray bricks.
So the computer scans through all those numbers and finds like, oh, here's a bunch of numbers that make a straight line, or here's a bunch that form a curve.
Exactly. It's like finding all the straight edge Legos, or all the round Legos, or all the bumpy Legos in the giant pile. These basic features are the building blocks, the first hints of structure within the sea of numbers.
So it's almost like a child learning to draw. They start with lines, then curves, then combine them to make a face or a house.
That's a brilliant analogy, Alex. Now, once the computer can identify these basic features, the lines, the curves, the specific patches of color or texture, it then needs to learn what combinations of these features make up something specific, like a cat or a dog. This is called training.
Training? How do you train a computer to recognize a cat? Do you show it a cat and say, good computer, that's a cat?
Not quite like training a puppy, though there are some similarities in the repetition. Imagine you're teaching our friend who can only count and follow rules to identify different types of fruit. You can't just say apple, you have to give them examples and point out the distinguishing features.
Okay, so I'd show them an apple and say, see, it's mostly round, it has a smooth, shiny skin, usually red or green, and there's a little stem at the top.
Exactly. And then you'd show them hundreds, maybe thousands of different apples. Some red, some green, some big, some small, some with bruises, some without. And with each one, you'd confirm, yes, this is an apple.
So I'm just telling it, this is an apple, this is an apple, this is not an apple.
That's the core idea of training. For a computer, you feed it vast amounts of data, thousands, even millions of pictures. For each picture, you've already labeled it. This is a picture of a cat. This is a picture of a dog. This is a picture of a car. And importantly, this is a picture of nothing important.
And what does the computer do with all those labeled pictures?
It starts its incredibly meticulous work of counting and finding patterns. It looks at all the pictures labeled cat. It picks out all the basic features, the lines, the curves, the textures, and it starts to notice which features and which combinations of features appear most frequently in the cat pictures and which don't appear in the not cat pictures.
So it's like a super organized librarian sorting through billions of tiny facts.
Yes, a librarian who is also a master detective. It might notice, okay, in pictures labeled cat, I frequently find two small triangular shapes near the top of the image, two round shapes just below them, and a fuzzy texture all around. And these patterns are rarely seen in pictures labeled car or tree.
A recipe book? I like that. So it's like a chef learning to make different dishes. They're given a recipe, here's how to make a cake, and they follow the steps, measuring ingredients, mixing them, baking, and they do it over and over until they get it right.
It's very similar. Each labeled picture is like a perfected recipe example. The computer is learning the ingredients, the features, and the steps, how those features are arranged and counted, that define a cat recipe or a dog recipe. This rule book or recipe book that the computer builds is what we call its model.
So the model is like the computer's brain, or its knowledge of what things look like based on all its training.
Exactly. It's the collection of all the patterns and rules it has derived from the millions of examples it's seen. Now, once it has this model, this recipe book, it's ready for the exciting part.
Prediction? You mean it tries to guess what something is?
That's right. You give it a brand new picture, one it has never seen before, and say, "Hey, computer, what do you see here?"
And it doesn't have a label for this one, so it has to figure it out itself?
Precisely. The computer takes this new picture, turns it into that grid of numbers, and then starts looking for those basic features, the lines, curves, textures, just like it did in training. But this time, it's not learning, it's comparing.
Comparing to its recipe book?
Yes, it compares the features it finds in the new picture to all the patterns and rules in its cat recipe, its dog recipe, its car recipe. It literally asks itself, how many of the cat features do I see here? How many dog features? How many car features? It's still counting and finding patterns, but now it's matching them against what it already knows.
So if it finds a lot of cat features and patterns, it says, this looks most like a cat.
That's the essence of it. It calculates which recipe this new picture matches most closely. It doesn't say it is a cat, but rather, based on my training, there's a 98% chance this is a cat, or a 2% chance it's a car, and a 0.5% chance it's a tree. It gives you a probability.
Wow, that's so different from how I think about seeing. I just see a cat, no percentages. But for a computer, it's all about the numbers and the likelihood.
And that's why this technology is so powerful. Because it's based on rigorous patterns and probabilities, it can be incredibly accurate, especially when trained on massive amounts of data.
So if it makes a mistake, like it sees a really fluffy dog and thinks it's a cat, how does it get better?
Great question. That's where humans, or sometimes even other AI systems, come back into the loop. If the computer makes a mistake, we give it feedback. We say, "No, computer, that wasn't a cat, that was a dog." This feedback is then used to refine its recipe book or its model.
So, it's like a chef getting feedback on a new dish. This cake needs a little more sugar, or the texture is a bit off, and they tweak the recipe for next time.
Exactly. The computer adjusts its internal rules, strengthens some connections, weakens others, so that next time it sees a similar fluffy dog, it's more likely to identify it correctly. This iterative process of training, predicting, and refining is how computer vision systems constantly improve.
So, from identifying objects in our photos to helping self-driving cars see the road to doctors analyzing medical images, it's all about this fundamental idea of computers counting patterns and matching them to learned rules.
You've got it, Alex. It's an incredible testament to how breaking down complex problems into simple, repeatable, numerical steps can lead to truly intelligent behavior, even without eyes or a brain in the human sense.
This has totally changed how I think about computers and vision. It's not magic, it's just incredibly clever counting and pattern matching.
Precisely. And it shows us that sometimes the simplest ideas, when applied consistently and at a vast scale, can lead to the most profound advancements.
Jamie, this has been an absolutely fascinating journey into how computers see the world. Thank you for making such a complex topic so clear and understandable.
My pleasure, Alex. It's always wonderful to explore these amazing technologies with curious minds like yours.
And thank you, our incredible listeners, for joining us on this exploration. Keep asking questions. Keep being curious.
Until next time, keep observing the world around you. And remember, even the most complex things can be understood by breaking them down into simpler parts.
Goodbye.
Bye for now.